Well, I already told you, we're going to play with outcome x1. And we're going to see how that affects the lottery, and something strange will happen. And I'll illustrate using this figure. First, I'm going to reduce x1, make it a bit smaller. Of course, the lottery, you like it less because one outcome has been decreased, but also the area has decreased. So it's perfectly natural. The natural thing is happening here. Lower value, worse lottery, less area, everything normal. Good thing. I keep on decreasing x1. Nothing special is happening. Always the value of the lottery is decreasing. What else would you expect? Now you see I'm getting very close to x2. x1 is only one infinitesimal step away from x2. Then I make the last step and I exactly decrease x1 so much that it hits x2. It now becomes identical to x2. Then I say something weird is going to happen. I'll show on this figure what happens. So here we are. We are at the moment x1 has hit x2. x1 is now identical to x2. First thing I'm going to do is remove this line, because now this is one outcome, x1 equal x2, one layer with one probability, p1 plus p2. So in this formula, I should normally write them separate, but they are together. I should write it as a w of p1 plus p2 times x1. That's the formula to be used now. And you may remember we were assuming w of p1 plus p2 is bigger than wp1 plus wp2. So this layer is much broader. So I add this red area underneath. This is how much wp1 plus p2 exceeds over wp1 plus wp2. This is just an additional area coming. A very small change of x1, an infinitesimal step so that it hits x2, and we have suddenly a whole explosion of new area. And that is really something that is not nice. First, it's a violation of continuity. A small infinitesimal change should not change much in the value of the lottery. It should not suddenly have a whole explosion of change. But even worse than that, it is a violation of stochastic dominance. We are decreasing an outcome and we're getting a higher value of the lottery. The value of the lottery has increased. That doesn't make sense. If you decrease the lottery, every sensible theory, I know empirically every weird thing happens. So there are situations in which people violate stochastic dominance. It can even be done in systematic manners by very clever experiments, but it doesn't happen in this way, as this theory says. This theory says always, if it is a configuration like that, always suddenly people will like a lottery much more if the outcomes collapse this manner. That's not happening empirically, not like this. So no theory should have a property like this, and this phenomenon invalidates the theory for empirical purposes. Well, so now I've shown you the case 1 where WP1 plus P2 is bigger than WP1 plus P2 gives anomalies. It doesn't work. The other case is similar. I will not spend much time on it. In that case, you have to not move x1 down to x2, but you move x2 up to x1. And then the moment where it hits x2, you get an implosion of area. That is then again a violation of continuity, and even worse, it's a violation of stochastic dominance, because improving an outcome leads to a worse value of the lottery in a way. Well, I know these things happen empirically, but not in the way that this theory says, not in this systematic manner, always like that, absolutely not. So this property really invalidates the theory for normative purposes, surely, but also for empirical purposes. So that's a big problem. So this became understood at the end of the 1970s when Kahneman and Tversky published their paper. And well, the conclusion is that old formula is just no good. It doesn't work. We need a better formula. So it was first when Kahneman, already in Fishburne, there was a paper by Honda already preceding Kahneman and Fishburne, Kahneman and Tversky a bit. And Fishburne already, he is a very good mathematician. He passed away recently, unfortunately, but he was a brilliant mathematician. He immediately, when he saw the formula, this cannot be. This is violation of stochastic dominance. So he immediately wrote a letter to the journals saying, guys, this does not work. And Kahneman and Tversky, actually, they were aware that of this problem. They tried to fix it, but they couldn't do it very well. So they kind of, tried to live with it, but they didn't really have the solution. So in the end of the 1970s, the situation was I still think that the intuition of psychologists, that how people feel about probability has more to do with risk attitude and how people feel about outcomes. Empirically speaking, that psychologist is absolutely right. We need to get that in a theory that stays. But the almost only natural formula that people could think of just doesn't work. We need a better formula. We need somebody to invent a clever theory that captures psychology, and that's typical of behavior. You have you have the psychological insights, but you also have the theory that connects with it. That connection is the typical thing. And here, to develop such a theory, if the psychologist's brain tell what happens empirically, then you need a clever theoretician. That's more often economists who bring that. That happened indeed. In this case, there were John Quiggin, in fact, David Schmeidler independently for the more difficult context of uncertainty. It was more subtle there. David Schmeidler independently developed basically the same idea as John Quiggin for uncertainty. We'll talk about it later. But for risk, we talk about now. John Quiggin did it especially for risk. And that was the rank-dependent idea. That was this very good idea to bring, to make theory connect with psychological reality. That I'm going to explain next, but that will be in the next recording.